let us say that you have a inclined plane over which you have a thin film of liquid of film thickness H, uniform film thickness H. So, here there is some liquid and here there is air. So, this line which is at the top is the interface between the liquid and the air. Gravity is acting like this and the inclined plane makes an angle theta with the horizontal, and pressure at air at all locations is P atmosphere. So, you have even like the left of the film P atmosphere, the right of the film P atmosphere, like that, and this is just a liquid film. So, if H is very thin, it is known as a thin film flow, and we will like to see that what kind of velocity profile in the film you get in this case. And again let us assume steady, constant property and fully developed flow. These are the three assumptions that we are considering here also valid. So, let us write the momentum equations. The continuity, what is the consequence of the continuity equation? So, let us set up the coordinates. Most of the things are very similar to what the two cases that we have already done. So, we will summarize that. So, let us say that this is like x axis and this is like y axis. So, what if you try to use the continuity equation, then what is the consequence of the continuity equation? V is identically equal to 0 for fully developed flow. So, the situation does not change here. Why? You have the continuity equation for incompressible flow equal to this. For fully developed flow, u is not a function of x. So, that means v is not a function of y. So, here you are not maybe sure about the interface between the liquid and the air, but the bottom wall at least you know that at y equal to 0 v must be equal to 0, no penetration boundary condition. So, at y equal to 0 v equal to 0, this means v equal to 0 for all y. So, you are having to deal with a situation where you have only u as the velocity component. Again we are modeling it as a 2-dimensional flow. So, the third dimension perpendicular to the plane of the board is quite large in comparison to the x and y dimensions. So, if we write the y momentum equation, so again it will look like the same as what we did for the Poiseuille flow. So, we are just summarizing it. Left hand side you have all the terms involving the gradients of v, so that those are 0 because v is 0, then minus this plus again all the terms involving v plus the body force along y. So, what is the body force along y? So, minus rho g cos theta. So, you have P equal to minus rho g cos theta into y plus some function of x. Then our more important concern is the x momentum equation. So, let us write the x momentum equation. So, if you write the x momentum equation for steady flow, so you have rho, for the steady flow the unsteady term goes away. So, anyway let us write all the terms and see which term goes away. So, this is y momentum, now we are looking for x momentum. Then what is the body force? What is the body force here? Rho g sin theta, it is along positive x. G sin theta is along positive x. So, now let us see which terms are there and which terms are not. First of all, because of steady flow this term is 0. Then fully developed flow means this term is 0 and V is identical equal to 0. So, left hand side again has become equal to 0. Since fully developed flow, you have the second order derivative of u also with respect to x 0 and u is a function of y only. So, this becomes the ordinary derivative d2u dy2. So, you have mu d2u dy2 is equal to now what is dp dx? dp dx is df dx basically. Now one important assumption is that you have this gap h is very small, so that we call as a thin film. So if h is small, what is an important consequence? The effect of the body force along the y direction is not important, because of the very thin gap the effect of gravity within a thin gap is not important. So because h is small, this particular effect is small. That means Fx is approximately equal to P, or for a thin film it is as good as P, there is no difference. So you have basically this is equal to dP dx minus rho g sin theta. So you can write it a bit differently, you can write mu d2u dy2 plus rho g sin theta is equal to dP dx, right. Again you see the left hand side you can write as function of y only. Of course this is like a constant, but it constant is a special case of function of y. So this is a function of y only, this is a function of x only, and this implies each must be a constant. So when each is a constant, then dP dx is a constant means what? Let us say that L is the total length of this. dP dx is a constant means the variation of pressure with x is linear. So if you say that the left end is 1 and the right end is 2, then basically you have dP dx is what? P2 minus P1 by L. Now from the boundary condition you see that both P1 and P2 are P atmosphere, right, because it is exposed to an uniform atmosphere. So this is P atmosphere and this is P atmosphere, therefore C is equal to 0. Okay. So this is a case where C is equal to 0, but the way in which the flow is driven is because here the gravity acts like a driving pressure gradient. So it's, we have seen that it's a piezometric head that is important, and the gravity part of the head is giving the piezometric head. So it's from a higher elevation to lower elevation, and that is what is driving the flow. That is what is like a equivalent negative dP star dx. If you include this in the P star, although P change is not there, but the gravity effect is there. And then like it is very easy and straightforward to integrate it twice to get the velocity profile. We are not repeating anymore, but what we will now try to pinpoint is what will be the boundary conditions. See, many problems have same governing equation, but the solution of one problem differs from the other through the boundary condition. So let us try to see that what are the boundary conditions here. So let us write the boundary conditions. So boundary conditions. What are the boundary conditions? At y equal to 0, what is the boundary condition? Yes? What is the boundary condition at y equal to 0? U equal to 0, that is fine. What is the boundary condition at y equal to h? Yes? Why du dy equal to 0? Yes? Who says that there will be no shear stress here? God has said that there will be no shear stress here. Where from you get that principle? Which fundamental principle tells that there will be no shear stress here? Which fundamental principle you tell? There is no such fundamental principle. The fundamental principle is like this. Here you have two fluids, air is a fluid and this liquid is a fluid. So fundamentally it is like a problem where you have say fluid 1 and fluid 2. You are thinking about the interface condition. At the interface what should be the condition? You have a continuity in certain things. What are the things which are continuous? First of all, velocity is continuous, because at a point you cannot have different velocities when you consider two different fluids. So velocity at fluid 1 is equal to velocity at fluid 2 at the interface, but that is something what is right, what we can't use here because we do not know what is the velocity. The other thing is that there should be a continuity in shear stress, because whatever is the shear stress at at the interface in the fluid 1 side, same shear stress should be there in the fluid 2 side. So it is a continuity in the shear stress, because at a particular interface there cannot be different momentum transport at the two sides. So the shear stress must be continuous. So the continuity in shear stress means here it is just a one dimensional type of flow, that means mu du dy must be continuous. So at y equal to h you must have mu of the liquid into du dy measured from the liquid side at the interface is equal to mu of the air into du dy at the air, okay. Because the viscosity of air is much less than that of the liquid, mu a is much less than mu l, this term is much less, that is mu a by mu l. If you write, this term is so small that it multiplies with whatever, that smallness remains. So this becomes as good as du dy is equal to 0. So whatever you have said du dy equal to 0 here as a boundary condition or equivalently 0 shear is correct, but in an approximate sense. If I now replace air with another liquid, then you will be in trouble, because then you, if you do not know what is the fundamental principle from which it comes out, still you will write a wrong thing. So important is the fundamental principle is continuity of the shear stress. Here the special case is just because air, it is a coincidence that air has much less viscosity than the liquid water, say this is water. So roughly like 1 by 1000. So then in that case this right hand side is so small that we can say that it is as good as 0. So now the two boundary conditions are at y equal to 0, u equal to 0, and at y equal to h, du dy equal to 0, and then based on these boundary conditions you can integrate this to get the velocity profile. That I am not going to do, very simple exercise. Okay. Now what we will do is we will see the consequence of having two fluids which are such that the viscosity of one is not negligible in comparison to the other. So we have seen one such movie earlier, and what we will do is we will look into the one of those movies again. So let us look into one of those movies where we were basically looking into viscosities, effect of viscosities of a two layered fluid. So just try to see that you have a two layered fluid, you can just perceive from the difference in color that you have two different layers, and just colored dyes are there, two different colored dyes are there in the two fluids to indicate the velocity profile. And you see that the velocity profiles are such that at the interface there is no continuity in the slope, that is du dy is discontinuous at the interface, that you can clearly see. The reason is it is not the continuity of du dy that is important, continuity of mu into du dy. because mu of the two fluids are different, du dy at the interface has to be adjusted. So when you have such two different fluids with two different viscosities, you should not look for a continuity in du dy, you should look for a continuity in mu into du dy, that is what is the important thing. Okay. Now let us come back to what we were discussing, and we will now try to look into one example problem where we will use a different coordinate system. So till now we have used the Cartesian coordinate system to solve certain problems. Now we will come to an example 4 and then subsequently one example 5 where we will be using a different coordinate system, and the choice of the coordinate system is often driven by the geometry of the flow. So here what we are going to do is we are going to discuss something which is very important from engineering applications, fully developed flow through circular pipes. So that is known as Hagen-Poiseuille flow. That is basically fully developed flow through circular pipes or tubes or whatever. So let us say that we have a circular tube or pipe like this. When we draw it, it looks like a parallel plate channel, because of course we are drawing the projection of it in the plane of the board. But keep in mind that we are talking now about a problem with cylindrical symmetry, where because the pipe surface here we are talking about is a circular cross section. So you have a pipe of, say, maybe we are talking about an axial length of L and fully developed flow. So the coordinate systems what we use for this case are the cylindrical polar coordinate systems, I mean, which are more common. So you have small r as the radial coordinate, z as the axial coordinate, and if you take the cross section of this, so if you draw the separately the sectional view, it is a circle. So the cross section wise the coordinate system is a polar coordinate system. So at a point if you consider it is r comma theta, so this is r and this angle is theta. So the coordinate system requires r, theta, z, and these are again mutually orthogonal coordinate system, because theta direction is perpendicular to r and r is perpendicular to z, and that means you have now r, theta, z, all these are basically mutually orthogonal to each other. Now we will be using therefore now the Navier-Stokes equation in the r, theta, z or the cylindrical polar coordinate system. So already we have communicated the corresponding forms of the equations through the course website. You must have those equations with you. Important thing is it is not necessary that these equations you have to remember. We will provide all these equations to you, I mean, during exams and so on, because our test is not whether you can remember these equations. So whatever is there with you is something what you will have if there is a question related to that, it comes in the exam. Our important objective will be how to simplify those equations and come to the solution of this problem. So let us look into some of those equations. I will project those equations in the screen so that which are already there, and it will be possible for you to follow it easily. So let us look into the cylindrical coordinate form of the Navier-Stokes equation, and we will try to solve the Navier-Stokes equation with the cylindrical coordinate form. To do that, we will always start first with the continuity equation and see that what the continuity equation gives to us. So let us look into the continuity equation form in the cylindrical coordinate. So if you look into the continuity equation, if you look into say the slide, the second equation. So the first term is that the density variation with respect to time. So we are considering a constant density fluid, so that term goes away. So let us see what the continuity equation gives to us. Okay. Next let us come back to the slide again. See the second term in the continuity equation. The second term it remains, because we are not very sure that what is going to be there. So 1 by r ddr of r into rho into Vr, rho r Vr. So that is the term. And what about the third term? So you have a third term. What about this term? First of all, rho is a constant. So rho is a constant and hence it comes out of the derivatives. So here also rho comes out of the derivatives. Then this term boils down to what? It boils down to the derivative of the gradient of Vz with respect to z. Okay. What is a fully developed flow? See, here also the concept of parallel plate channel does not change. That is, you have the boundary layers which are merging, and beyond that the velocity profile whatever is going to be there, that does not change further with the axial coordinate. The axial coordinate is the z coordinate. So that means Vz is the velocity component along the axial direction, that does not change with the z coordinate any further. So fully developed flow means this is equal to 0. Just like du dx was 0 for parallel plates, here just replace u with Vz and x with z, axial coordinate. So then you are left with ddr of rvr, that is equal to 0, right. We are not considering that singular case. See, these are the singularity at r equal to 0. So we are not considering that singular case, but for a general case. So r, that means r into Vr is not a function of r, right. Only way it is possible, there are two ways. So the first one way is if you do not look into the boundary condition, say you do not look into the boundary condition but you just want to look into this. So then if you have Vr equal to C by R of that form, but then that will be a conclusion made without looking into the boundary condition, because this has to be satisfied within the constraints of the boundary condition, not just as a general case. So what is the constraint of the boundary condition? That at the wall at small r equal to capital R, you must have Vr equal to 0. That is a no penetration boundary condition, that is the fluid cannot penetrate through the wall in the radial direction. So which means that you have, since at r equal to capital R Vr equal to 0, which means Vr equal to 0 for all r from this one except r equal to 0, that is a singularity, we are not talking about that. So whenever we are coming up with a solution, we are cleverly avoiding the singularity point, and then for the remaining, that from this, since this is not a function of r, basically you forget about the r equal to 0 case, that means it is as good as Vr not a function of r. So if you have found out that Vr equal to 0 at r equal to capital R, it should be 0 for all r. So from the continuity equation, our conclusion is that Vr equal to 0, just like V equal to 0 for parallel plate channels. Next we will go into the momentum equation. Let us say, so we have how many versions of the momentum equation? So if you see the cylindrical coordinates, you have the r, theta and z. So let us look into the case with theta. See, first of all, what about the derivatives with respect to theta? So if you look into these equations, you will see that there are lots of terms which are having derivatives with respect to theta. So if you want to figure out that what happens for the derivatives with respect to theta, you look into the equations very carefully. Now when you have derivatives with respect to theta, in all the momentum equations such terms are there. So terms of the form derivatives with respect to theta. Question is that when will it be 0? See, theta is what? Theta is the polar coordinate. So if you have a symmetry with respect to the axis, that means that is called an axisymmetric flow. Then the symmetry with respect to axis means that there will be no variation with respect to theta. It is only symmetric with respect to axis, at which theta it is located is immaterial. So axisymmetric problem will always mean this equal to 0. When you have axisymmetric problem which means that this equal to 0, you have to keep another thing in mind, that axisymmetric problem does not ensure that V theta equal to 0. You could still have V theta but that not a function of theta. So if you have a V theta component, it is something called as a swirl component because it tries to have a rotation or swirl in the flow. But here we are considering that there is no V theta. So if there is no V theta, I mean if you look into the continuity equation, see the continuity equation is satisfied. Let us go back to the continuity equation. You see that in the continuity equation there is a term dd theta of rho V theta. So that term we omitted because of the axisymmetry condition. So in the continuity equation we did not consider V theta, that does not mean that V theta is not there, simply the theta gradient of V theta was 0 because of the axisymmetric condition. So till now we have never utilized the condition that V theta is 0, but now we will utilize it by noting that it is not a swirling type of flow. There may be swirling type of flow in a pipe where there is a rotationality that is imparted to the flow, but here we are considering that such rotationality is not imparted to the flow, and that means you have for this problem, so no swirl is considered, that means you have V theta equal to 0. So you see certain conclusions are there, conclusions at the end are important, but where from you arrive at the conclusions I feel is even more important. So now we go back to the momentum equations again. So in the momentum equation let us look into the theta component of the momentum equation. So theta component of the momentum equation has all terms involving the derivatives with respect to theta, right, except in fact all. So the theta component of the momentum equation will have only one term which does not involve derivative with respect to theta. What is that term? So if you look into the theta component, so in the theta component the first term is dv theta dt is equal to 0, second term Vr dv theta dr equal to 0, because V theta is 0 that term is 0, third term has Vr and V theta, so when V theta is 0 that is equal to 0, fourth term also has V theta, so left hand side is 0, right hand side no p variation with theta, so that term is 0, next term you have a V theta, so although the arc derivative is there but because V theta is 0 that is 0, so if it is a swirl flow that term is not 0, but when there is no swirl that term is 0, remaining terms have either V theta or derivatives with respect to theta, either of those are 0, so it is like 0 equal to 0. So theta momentum equation does not give us anything for this problem. So then the R momentum equation, so let us look into the R momentum equation. So for the R momentum equation you see the first term is dVr dt, that is because of steady flow the first term is 0, second term Vr is equal to 0 identically, that you have to keep in mind because of fully developed flow. So that means the second term is 0 and the third term is 0, either way, either Vr 0 or the theta gradient is 0, either way it is 0. Fourth term you have a V theta square by r, V theta square by r is like the centripetal acceleration term, and because the swirl component or the rotational component is not there, the fourth term is 0. Then the fifth term Vr is 0, so that term is also 0, right hand side minus dpdr, now this term is there, so at least we have found out one term which is there, so minus dpdr, then next term is again 0 because Vr is 0, then the remaining term, so d2Vr d theta 2 that is 0, d2Vr dz2 equal to 0, dv theta d theta equal to 0, you have a rho Br. So rho Br is like if you have a body force along the r direction, so if you have a body force along the r direction then that is what is very much possible. So you see that there is only one component which is Vz and there is no Vz term in this, so you have basically the R momentum equation giving what, 0 is equal to minus dpdr plus rho into Br. Okay. Now we come to the Z momentum equation which is going to be the most important equation for our velocity profile solution, because our velocity profile is Vz. So look into the terms. First term, so we are talking about the last equation which is there in the slide. So first term, the unsteady term, it is 0, then next term is Vr is there, so that is 0, third term V theta is there, that is 0, fourth term V dVz dz is there, which is 0 for fully developed flow. So the left hand side has become 0, right hand side you have minus dp dz which is there. Next term, the first term is very much there because Vz as a function of r is what is reflected in that term, and second term in the square bracket Vz is not a function of theta, so that is 0, and the third term is 0 by fully developed flow. So we are left with the z momentum as 0 equal to minus this one plus mu into 1 by r, this into r plus okay, and where what will be Bz here. So if you have the acceleration due to gravity like this, so let us say that this axis of the pipe is inclined at an angle theta with the horizontal, so you have this angle as theta and this angle as 90 minus theta. So you have a Br as, so Br as minus g cos theta and Bz as minus g sin theta. So this is minus g sin theta. Okay. So the forms of the equations that where we have arrived are something which are very much similar to what we had arrived for parallel plate channels. Only because of the cylindrical symmetry you have this 1 by r ddr, this type of term. So but if you write it in the divergence form, in the vector form, or here the Laplacian operator form, then that is basically identical. So vector form is identical just because of the shift of the coordinate system. That is what the second derivative of Vz with respect to r looks like, whatever was there in the Cartesian system equivalent in this cylindrical system. Okay, so we stop here now and we will continue with this in the next class. Thank you.